In this tutorial we're looking at section 11.2 on growth and decay. So growth is modelled by the equation n equals n naught e to the kt, where n naught is the initial population, t is the time, k is the annual growth rate, n is discrete and needs to be rounded when giving final solution. Because we're talking about usually populations, hey, we can't have half a person, that's the thing, so we need to round off accordingly. For radioactive decay, we have m equals m naught e to the negative kt. So m naught is our initial mass, t is time, and k is our rate of decay. So this time we're going to be having our population or amount of mass decrease. Okay, our half-life t is the time taken for half of the original mass to decay, and t is given by t equals 1 on k log to the base e of 2. Okay, our half-life doesn't depend on time whatsoever. Okay, it's actually independent of that. Doesn't matter how much you've got. Okay, your half-life will be constant. Okay, typically things can have half-lives of a millionth of a second to millions of years. Okay, now you'll see if you have a look at the textbook that this looks like it's awfully condensed. Okay, they go through using our first and second order differential equations to get to these results, but there's not a lot of point in actually going through that process when you can just use the equation that we're given. Okay, so we'll have a look at some worked examples. So worked example 1. Okay, the population of a certain town increases at a rate proportional to the current population. At the start of 2000, okay, so the year 2000, okay, our population was 250,000. Okay, in 2008, okay, our population was 750,000. Okay, we want to express the population number in millions, n. So n is in millions. Okay, in terms of t, okay, so we're going to have an equation in terms of n and t, okay, where t is in years. Okay, well, we know that we can use the equation n equals n naught e to the kt. Well, we know our initial population. That was 250,000. Okay, but we need it in millions, so we can say n naught is 0.25. So we can say n equals 0.25 e to the kt. Okay, we need to work out what this k value is. That's where we can use our second bit of information. So now we can say, well, 750,000, which is 0.75, here's 0.25 e, well, our t is 8 in that example, so it'd be 8k. Okay, so we can rearrange this, okay, and say, well, we get 3 equals e to the 8k, so log to the base e of 3 equals 8k, so k equals 1 on 8 log to the base e of 3. So k is approximately 0.1373. Okay, so that means that our n of t is equal to 0.25 e to the 0.1373 t. Okay, part B is what is the predicted population at the start of 2016. Okay, we simply need to put into our equation t equals 16, so you get n of 16 equals 0.25 e to the 0.1373 times 16. Okay, when we do that, we get a value of 2.25 million. Okay, people. Okay, part C is in which year does the population reach 5 million? So this time we're going to be solving for t, so we're going to be saying, well, we want 5 million, okay, and we've got that's equal to 0.25 e to the k, sorry, to the 0.1373 t, okay. So that means we divide by our 0.25 and we say, well, 20 equals e to the 0.1373 t. So log to the base e of 20 equals 0.1373 t. Okay, which means we can say that log to the base e of 20 divided by 0.1373 equals t. So t equals 21.815. Okay, so it's part way through that year, okay, which means it's in the year 2021. Okay, it's towards the end of the year, but it's within that year. Okay, so we don't actually round up to 22, okay, in this case, because in the year 2021. Okay, so we'll keep moving on and we'll have a look at worked example 2 and 3. So worked example 2, the rate of decay of a radioactive substance is proportional to the amount of the substance present at that time. Initially 30 milligrams of a radioactive substance is present. After 2 hours, the experimenter observes that 20% has disintegrated. Determine the amount remaining after a further 3 hours, correct to 3 decimal places. Well, what we said before, if we have a look back here, okay, is that for our radioactive decay, it's m equals m naught e to the negative kt. So we can say m equals m naught e to the negative kt. Okay, we know we had an initial amount of 30 milligrams. Okay, so that's our m naught. M naught equals 30. Okay, so what we can do then is say, well, m equals 30 e to the negative kt. Okay, well, we know after 2 hours, okay, we've lost 20%. Okay, so what that means is, well, 10% is 3, so 20% off is going to be 6 off, so we're going to say, well, 24 equals 30 e to the negative 2k, okay, because our time is 2 hours. Okay, so from here we're going to be able to work out what our k value is. So what we're going to do is go 24 over 30 is equal to our e to the negative 2k. So we can say our 4 on 5 is equal to e to the negative 2k. So log to the base e of 4 on 5 is equal to negative 2k. So k is equal to negative a half log to the base e of 4 on 5. Okay, so when we work that out, k is approximately equal to 0.1116. Okay, so that means our equation is m equals 30 e to the negative 0.1116 t. Okay, and we also need to determine the amount remaining after a further 3 hours. So what that means is we need to sub in t equals 5. Okay, because we're at t equals 2 before, okay, well, after 2 hours, and then saying after a further 3 hours. So we're actually talking after 5 hours, so we say m equals 30 e to the negative 0.1116 times 5. Okay, when we work that out, we find that it's 17.173, okay, and that'll be milligrams, okay, after 5 hours. Okay, so we'll have a look at worked example 3 as well. So it takes 2 years for 30% of a particular radioactive substance to disintegrate. Determine the half-life of the substance correct to 3 decimal places. Hey, well, we know that T equals 1 on K log to the base E of 2. Okay, so that's fine, but we don't know what our K value is. So what we need to do is look at our M equals M naught e to the negative kt. Okay, and we know it when we have after 2 years, so when t equals 2, okay, that m is going to equal 0.7 m naught, or 0.7 times the original amount, because we've lost 30%. Okay, so what we do is we can set up our equation and say, well, 0.7 m naught equals m naught e to the negative 2k. So what that means is we can divide by our m naughts and say, well, we've got 0.7 equals e to the negative 2k. So log to the base e of 0.7 equals negative 2k. So k is going to equal negative a half log to the base e of 0.7. Okay, so k is going to equal 0.1783. Now we have our k value, we can stuff it in here and say, well, t equals 1 on 0.1783 times log to the base e of 2. That means t equals 3.887, okay, which is in years. Look, I don't think you'll have too much trouble with these questions. We've done very similar ones in our study of maths methods so far, so I think you'll get through all these questions without too many dramas.